Hi everyone and welcome to my YouTube channel. So the time has finally come and now we'll be moving into much harder functional equations. So far we've solved around 16 functional equations that were classified as easy. We learned the basic principles like injectivity, surjectivity and some substitution tricks like the circle method and cancelling method and other methods as well. And now we'll be moving into much harder problems, and in this video we'll be solving a problem from the IMO 2017 problem 2. So in fact this problem is hard, is classified as hard. So for example, in the exam or in the contest you were given 6 problems, 3 problems at the first day, at day 1, and 3 problems at day 2. Problem 1 and problem 4 are easy, problem 2 and problem 5 are medium, and problem 3 and problem 6 are hard. So in the IMO 2017, actually the participants who solved problem 1 and problem 4 and problem 2 completely, they took silver medal. So you can imagine that if you actually can solve this problem by yourself, then you can even win a silver medal in the IMO. So if you're just as excited as me, so before we start with the problem, I recommend that you try the problem yourself and then come to see the solution. In this way you can test yourself and see your level or what you can find actually in this functional equation, because don't expect this problem to be as previous problems because it is much harder. In fact, I call this problem the injectivity battle. So this problem is all about proving that our function f is injective. If you can prove that your function is injective, then you are done. If you can't, then you will lose some marks or maybe you will get 0 if you don't conclude anything. Okay, so let's start with our functional equation. So find all functions f from R to R such that, and we have this small functional equation, f of x times f of y plus f of x plus y is equal to f of x times y. Okay, so the first thing that we notice here is that unfortunately we don't have any free quantity. So for example, in previous problems we had, for example here, plus x or times x plus y. So that was a free quantity, so we can use it to prove surjectivity and injectivity. But now we don't have any free quantity. In fact, every term here, each term is contains f. So here we have f of something, here we have f of something, here we have f of something. So this is much more harder to handle. But let's take a look. Can we substitute some small numbers? So for example, if we substitute here, can we substitute y with 0? Well, actually, this will be f of 0, this will be f of x. The problem is where this is nice, but this is very ugly because it's f of x times f of 0. And that's weird because you can't get any useful information because you have f of x times f of y. So this is the problem here. This is nice and this is nice. So what can we do here? If we can't substitute with small numbers, what can we do? Well, actually, there is a trick or a method that we discussed earlier in previous videos. In one of the videos, we discussed a whole problem using one method, and you can use this method here. So can you guess what is this method? Well, take a look. Here you have f of something, and here on the left hand side, and on the right hand side you have f of something. So the method that you can use is the cancelling method. The cancelling method makes sense because you have f of x plus y here, and here you have f of x times y. So if you make x plus y equal to x times y, then this will be cancelled and you will get some nice property, f of this equals 0. Okay, so now we can start with the cancelling method. Okay, so we want x plus y to be equal to x times y. So actually, let's do this. Let's solve for y. We want x plus y is equal to x times y. Let's find the value of y. Well, y is, this will be x times x minus 1. Okay, so if we substitute now x, p, x, and x over x minus 1, then this will be cancelled with this, and we will get f of x times f of x over x minus 1 is equal to 0. But, however, you need to pay attention that the denominator can't be 0, so x can't be equal to 1. So x is any real number that is not 1. So you need to pay attention to it. Okay? Okay, so now let's do this substitution and get something useful. So now we will substitute p, x, and x over x minus 1. Let's see what we will get. So we said that this will be f of x plus y is equal to f of x times y, because this is the main thing here. So in fact we will get the following: f of x times f of x over x minus 1 is equal to 0. Okay, so now we have this nice functional equation. Okay, so what now? You have f of x times f of x over x minus 1 is equal to 0. So the first step is done. But what is the second step? What can you do here? Because the same is still here. If you substitute x with 0, for example, f of 0 squared is equal to 0 is useless. So you need to make something clever here. In fact, you can use this by its own to get a very nice thing. So can you figure out what can you substitute x with to get a very nice property? Well, I want you to imagine you have f of something is equal to 0, right? So let's take a simpler example actually. Let's assume that we have f of x is equal to 0. Assume that we have this. And now what we can do here, since f of x is equal to 0, we can substitute x with f of x. If we substitute x with f of x, then we will get the following: f of, and here f of x equals 0, right? But notice that f of x is already 0, right? We substituted x with f of x, and so now we have f of x, but f of x is 0, so we now have f of 0 equals 0, right? You see? So we started from this and we got f of 0 equals 0. So can we do the same here? The same idea, can we apply it here in our functional equation? So it's just like substituting the functional equation with itself. So what we'll be doing here is substituting x with f of x times f of x over x minus 1. So it's pretty complicated, but once you understand it, it's very simple. We want to substitute x with f of x times f of x over x minus 1. So now f of x, now here this f of x, what will f of x be equal to? It will be equal to f of this thing. But notice that f of this thing is 0, right? So we will get f of 0 times something. So f of 0 equals 0, right? So now actually we can evaluate f of 0, right? So by simply substituting x with f of x times f of x over x minus 1, we now have f of 0 is equal to 0. Okay, I'll repeat it again. Here we substituted x with f of x times f of x over x minus 1. So this f of x will be 0. Okay, so this will be 0. So now we have f of 0 equals 0. So that's great. Now we have shown that f of 0 equals 0. So now at least we have some information. Okay. Now let's go back to our original problem, our original functional equation. Let's substitute, for example, y with 0. So we will get f of 0, which is 0. Okay. And here you will have f of x. And here you simply have f of y is 0. So this will be f of 0, which is 0. So you simply have f of x equals 0. So in fact, let's now substitute px0, because we know the value of f of 0. We said that f of 0 is 0, and f of 0 is 0, so this is cancelled. Now this is f of 0, so it's 0. So here you have simply f of x is equal to 0. So we have actually found our function. It's 0. So let's now check out that this function works. So 0 plus 0 equals 0, and indeed it works, and so we're done. No, we're not done yet. If you thought that we are done, then you've fallen in the trap. In fact, this is only the introduction of the problem, the thing that we did earlier. But what is the mistake that we made? In fact, if you believe that our solution was right, then check out the function f of x is equal to 1 minus x. In fact, this is a solution to our problem, but what we got earlier is that the only solution is f of x is equal to 0. So how can this be here? Check that 1 minus x is a solution. So here 1 minus x times 1 minus x, multiply them by each other, and then take 1 minus this, and do the same for the other things, and you will get that this is a solution. So there must be some problem that we didn't mention, that we forgot to mention. Okay, but what is this problem? So the thing here is, first of all, what we did was to take x plus y equals x times y, which was very logical, and there was no mistake here. We reached this identity, f of x times f of x over x minus 1 is equal to 0. Okay, then we substituted x with f of x times f of x over x minus 1. And here is the problem. Can you figure out what the problem here is? Well, actually this functional equation, or this property, is true only for values of x that are not 1, right? Because the denominator will be 0. So when you substitute x with anything, then you should pay attention that this thing is not equal to 1. So what if this f of x times f of x over x minus 1 is 1? If this is 1, then you can't substitute x with this thing, right? Okay, so that is the thing that we forgot. So now let's discuss the two cases here. Okay, so we have two cases here. The first case is f of x times f of x over x minus 1 is equal to 1, always, for all real numbers x that are not 1, of course. Okay, so the first case is when this is 1. Now, in this case, we can't substitute x with this thing, because as we mentioned, this is true when x is not equal to 1. And the second case is when f of x times f of x over x minus 1 has only one number that makes it not 1. So for example, let's write it more formally. Case 1, let's write case 1 that we discussed. Case 1 is, assume that there is a number, let's say it's alpha, such that f of alpha times f of alpha over alpha minus 1 is not equal to 1. Okay? And of course, alpha is not equal to 1. If we have this alpha, if we have one alpha that satisfies this, that this is not equal to 1, then we can do the same thing. Then we can simply substitute x with f of alpha times f of alpha over alpha minus 1, and we will get that f of 0 equals 0, and we will get that f of x is equal to 0. Okay, so that's only the first case of the problem that we discussed. Now the second case is the harder case, which is what is the the opposite of this. If we don't have any value alpha such that this is not equal to 1. So the second case is simply case 2 is when f of x times f of x over x minus 1 is equal to 1 for all real numbers, of course, excluding 1. So this is the second case. F of x times f of x over x minus 1 is equal to 1. Because in this case, we can't substitute x with this because it is 1. And we now need to discuss this second case. So now let's erase everything and discuss this case in details. Okay, so now we'll be discussing the second case, which is f of x times f of x over x minus 1 is equal to 1 for all real numbers that are not equal to 1. This is the second case. Okay, but now actually look at this simple functional equation compared to this complicated functional equation. This is much more simpler. So what can we actually get from this functional equation, from this property of f? Well, you can get lots of things. You can evaluate, in fact, f of 1 and f of 0. But how can you evaluate f of 1? Well, do you remember that we said that f of this thing is equal to 0, right? We said we have written earlier that f of x times f of x over x minus 1 is equal to 0. But since this is 1, then simply f of 1 is equal to 0. So now we have f of 1 is equal to 0. Okay, so now we've evaluated the value of f of 1. What about f of 0? Can we evaluate the value of f of 0? Well, that's very simple. Substitute x with 0, and you will get f of 0 squared is equal to 1. So by simply substituting x with 0, we will get that f of 0 squared is equal to 1, which means that f of 0 has two cases, either minus 1 or positive 1. Now I want you to notice something nice in our functional equation. We don't need to discuss the two cases. We'll be discussing one case, and we'll apply the same for the second case. I want you to look at this, our original functional equation. In fact, if f is a solution, then minus f, negative of f, is also a solution. So can you prove this? This is very simple. Simply substitute each f with minus f. So assume that f is a solution, then minus f is also a solution because minus f times minus f is f times f. And this minus, and this minus, we can multiply by minus 1, and the functional equation will be true. So actually, we have the following nice property. If f is a solution, then minus f is also a solution. So we can only discuss the value of f of 0, one value, for example, f of 0 equals minus 1, and then we can do the same for the value f of 0 equals 1. Okay, so now we'll pick only one case, which is f of 0 equals minus 1. So let's say that f of 0 equals minus 1. We said earlier that 1 minus x is a solution. Then that means that x minus 1 is also a solution. So in this case, when f of 0 equals minus 1, then we have f of x equals x minus 1. Okay, so now we have these two values of f. That's very nice compared to when we start with the problem. Now we know that f of 1 is equal to 0 and f of 0 is equal to minus 1. Okay, that's very good. So what next? What can we do? Okay, so since we know the value of f of 1 is equal to 0, then we can simply now substitute y with 1 in our original functional equation because we know the values. So let's substitute y with 1 and see what we will get. So let's substitute p, x, and 1. Okay, so now here we have f of 1 is equal to 0. So this is f of 0, which is minus 1. So this very ugly term is now minus 1. This is f of x plus 1 and this is f of x. So now we have the following nice property, which is f of x plus 1 is equal to f of x plus 1. Okay? Now we have f of x plus 1 is equal to f of x plus 1. Now, I want to tell you something, that when you find this something similar to this relation, f of x plus 1 is equal to f of x plus 1, you can actually generalize this to more generalized property, which is that, in fact, f of x plus n is equal to f of x plus n. And here, n is any natural number. How can we prove this? Well, you can prove it by a simple induction. For example, you can apply this property n times. So f of x plus n is equal to f of x plus n minus 1 plus 1. And each time you can take a 1, take a 1, take a 1. You take n ones and you will get this. So now we have this nice property, f of x plus n is equal to f of x plus n. Okay, so that's nice. So now we have actually lots of information. We've evaluated the value of f of 1, the value of f of 0, and we have this functional equation. We have our original functional equation. So what we will do next? Well, I told you that this problem is all about injectivity. So actually, until now, we have just been doing something simple because we need to prove that our function is injective. Okay, so now we can divide the problem into two things. What we will do next, we can divide it into two sections. The first section is proving the injectivity of f. And the second section is using the injectivity of f to kill the problem. So now, actually, instead of starting with proving injectivity, I will delay that till the end of the things, the two sections, and I will start with assuming that f is injective. Then how can we solve our problem? Because it's much more logical. If you are in the contest, then you like solving the problem. You don't know if you can prove that your function f is injective or not. But when you arrived to a point that if your function f is injective, then you can kill the problem, then it's worth it to try to prove injectivity. So we will assume that our function f is injective, and we will solve the problem, and then we'll prove the injectivity. Okay, so that's what we'll be doing next. Okay, so now let's do the first section. We will assume that our function f is injective and solve the problem. Okay, I've written the information, the important information that we've proved earlier, so we don't forget them. F of 1 is equal to 0, f of 0 is equal to minus 1, and f of x plus n is equal to f of x plus n for any natural number n. And now let's solve the problem assuming that f is injective. Okay, so how can we now solve the problem? Well, now since we know the value of f of 1 and f of 0, it's very logical to take this f of x plus y and use it in our advantage. How can we do this? Well, you can make x plus y equal, for example, to 0, and make f of x plus y equal to 1. This will using the fact that we know the value of f of 1 and f of 0, then we can know the value of this f of x plus y. We will be left with this f and this f. Okay? So let's now start with substituting y with 1 minus x. So x plus y is equal to 1. Okay, so now let's start by substituting. px and 1 minus x. Okay, so now we have the following: f of x times f of 1 minus x, and we said that x plus y is x plus 1 minus x, which is f of 1, but f of 1 is equal to 0, so this vanished here. So now we have this is equal to f of x times y, which is x times 1 minus x. Okay, now do you know why we have assumed that our function f is injective? Exactly. We have now f of something is equal to f of something else. That means that something is equal to something else, right? Because our function f is injective. If f of a is equal to f of b, then a is equal to b. So now we can delete these two f's, this with this, and write the following result: f of x times f of 1 minus x is in fact equal to x times 1 minus x. And of course, this is very nice property, very nice result. So that's why we've assumed that our function f is injective, because if it's injective, then you can cancel these two f's together and to get this nice simple functional equation. Okay, but this is not enough to solve the problem. We need one more similar functional equation to solve the problem. Notice that we've only used x plus y is equal to 1. What about 0? So we'll substitute now p x and minus x. So this will be 0. Okay, so now let's write what we have. f of x times f of minus x is plus f of 0. F of 0 is minus 1. So this is equal to f of minus x squared, f of minus x squared plus 1, right? Okay, but can we do the same that we did here? Well, unfortunately no, because here we had f of something is equal to f of something else. Here we have f of something is equal to f of something plus 1. So we can't do the same here. Well, actually, you can do the same thing here. But how? You have f of something plus 1. Well, ladies and gentlemen, remember that we have this magical relation here. F of x plus n is equal to f of x plus n. Okay, but how can we use this to our advantage? Well, f of x plus any natural number can be grouped to one f. So f of x plus 1, f of minus x squared plus 1 is equal to f of x plus 1. So this is equal to f of minus x squared plus 1. Okay? This comes from this. So now we can apply the same thing. F of something is equal to f of something else. Now we can cancel the two f's and get a similar result here. So you see the importance of this? Okay, so now we have a similar property. Here we have f of x times f of minus x is equal to 1 minus x squared. So now we have everything we need to solve or to find the value of f. We have this and this. So try finding the value of f from these two equations. How can you find the value of f? Take a look. Here we have f of x times f of 1 minus x. So you have two variables. Here you have two variables, but f of x is the same here and here. So in fact, you have two equations with three unknown variables. Well, that's a problem because you can't evaluate or you can't solve two equations with three unknown variables. So in fact, they are not three unknown variables, they are two. Why? Because f of 1 minus x, again, we'll use this f of 1 minus x is the same as 1 plus f of minus x. and f of minus x is one variable. So now we have actually two variables here. Okay, so now let's start by dividing these two equations by each other. So f of x will be cancelled. So let's divide, let's give it a number, 1 and 2, and let's say that 1 divided by 2 will give us the following. First of all, we got rid of f of x. Now we have simply f of 1 minus x over f of minus x. But to make it only one equation with one variable, we said that f of 1 minus x is in fact 1 plus f of minus x. It all comes from here. F of x plus n is equal to f of x plus n. So now we have this 1 plus f of minus x over f of minus x is equal to, now let's divide this, 1 minus x times 1 plus x. So 1 minus x cancels 1 minus x. So that's very cool. X over 1 plus x. Okay, so now we can simply expand everything because you have one equation with one unknown variable. Okay, so now f of, you have 1 plus x, and this is equal to f of minus x times, here you have x, and here you have minus x plus 1. So this is x minus x plus 1, which means that f of minus x is equal to minus x minus 1. So now we've found the value of f of minus x. Well, that's the same as finding the value of f of x, because we can simply substitute x with minus x. So since we have this, we can substitute x with minus x to get the value of f of x, which is f of x is equal to x minus 1. Okay, so now we know that f of x is equal to x minus 1. Of course, you can check that this solution works here by simply substituting each x with x minus 1. And we said earlier that if f is a solution, then minus f is a solution. So if x minus 1 is a solution, then 1 minus x is a solution. That's the point where we said that f of 0 is equal minus 1 or positive 1. If it's minus 1, then you have this solution. The second case, when you have f of 0 is equal plus 1, is f of x equals 1 minus x. Okay, so now if our function is injective, then we have solved the problem. But is it injective? That's the battle. The battle starts right now. So ladies and gentlemen, let's start proving our function f is injective. So our claim now is that f is injective, and now we'll start with the proof. I remind you that I've written here the important information that we have concluded earlier. F of 1 is equal to 0, f of 0 is equal to minus 1, f of x plus n is equal to f of x plus n, and f of x times f of x over x minus 1 is equal to 1. And now let's start with proving injectivity. Okay, so the first thing we need is simple. We know that f of 1 is equal to 0, right? But we want to show that the only number x such that f of x is equal to 0 is 1. So how can we show that? So we want to show that f of x is equal to 0 if and only if x is equal to 1. We know that if x is equal to 1, then f of 1 is equal to 0. But what about the other direction? So let's now assume that we have some number alpha such that f of alpha is equal to 0 and alpha is not equal to 1. And we want to reach a contradiction. How can we reach this contradiction? Well, it's very simple. I want you to take a look at this box right here and show that. Reach the contradiction. Well, you can simply substitute, since alpha is not equal to 1, then you can substitute x with alpha, right? Since alpha is not equal to 1. And substituting x with alpha, this f of alpha will be 0. So 0 is equal to 1, which is a contradiction. So if we substitute x with alpha here, we will get we will get 0 is equal to 1, which is a contradiction. So in fact, we have shown that f of x is equal to 0 is equivalent to saying that x is equal to 1. So that's the first thing we need to prove injectivity. Okay, that's simple. What about f of 0? Can we show that f of 0 is equal to minus 1? We know that. Can we show that the only value that satisfies f of x is equal to minus 1 is 0? So we want to show the same thing. We want to show that f of x is equal to minus 1 if and only if x is equal to 0. How can we show that? Well, we will do the same thing. Let's assume that f of beta, let's assume that we have some beta here, such that f of beta is equal to minus 1 and beta is not equal to 0. Well, unfortunately, it's useless to substitute x with beta here. So we need some other trick, some nice trick here. Well, instead of using this, we will use this. We've used it many times until now. This f of x plus n is equal to f of x plus n. So let's use it again. How can we use it again? Well, we know this is true. So can we change or convert this into this? Well, yes, we can. Can you make this minus 1 0? Yes, we can, by simply adding 1. So let's add 1 to the both sides of the equation. So we have now f of beta plus 1 is equal to 0. And remember that f of beta plus 1 is f of beta plus 1. So this is the same as f of beta plus 1. Okay, now we have f of beta plus 1 is equal to 0, which means that beta plus 1 is equal to 1, which means that beta is 0. And so we're done. We reached a contradiction because beta is not equal to 0 here. So now we can write the other result, which is that if f of x is equal to minus 1 is equivalent to saying that x is 0. Okay, so those were not very difficult to prove. So those are the first two things you need to show to prove that your function f is injective. Okay, so now let's move on to proving injectivity. Now, if we want to prove injectivity, then it's very logical to take two numbers, a and b. So let's assume that we have two numbers, a and b, such that a is different from b, and f of a is equal to f of b. And we want to reach a contradiction. Okay? So a is not equal to b, and f of a is equal to f of b. Now, in fact, using this again for maybe for the fourth time or the fifth time, if f of a is equal to f of b, then we can say actually that f of a plus n is equal to f of b plus n. And in fact, not only natural numbers, but even for integers. So this is true not only for natural numbers, but even for integers. You can check that out. Okay, so now we can even have many other a's and b's, because we now have f of a plus n is equal to f of b plus n. Okay, so that's cool. Now, I think you have tried to substitute x with a and y with b and something like that. But unfortunately, this is really useless, because here you're going to have f of a plus b, and we don't know any information about f of a plus b. And here you have f of a times b, which is useless. Here you only have f of a times f of b, and it's also useless because it's just f of a squared, and you don't have any information. So what can we do? How can we solve, how can we prove injectivity or reach a contradiction? Well, here is the magical idea. The idea that will make us win in this injectivity battle. The idea is, instead of substituting directly x with a and y with b, we will take two variables or a pair of numbers x0 and y0 such that x0 plus y0 is equal to a plus 1 and x0 times y0 is equal to b. So like we want to introduce two indirect variables x0 and y0 such that if we plug x with x0 and y with y0, we will get a and b. Okay, so before taking this x0 and y0, what do you think we need to make x0 plus y0? A or a plus 1? And here x0 times y0. What do you want it to be? Well, let's assume that we can make this a plus 1 or a and this is b. So let's actually assume that we have two x0 and y0 such that x0 plus y0 is equal to a and x0 times y0 is equal to b. In fact, this is not very important or not very useful because of the following. Here, if we substitute x with x0 and y with y0, so b x0 y0, we will have, this is x0 plus y0, so this is f of a, and this is f of b, so those cancel each other because f of a is equal to f of b. So now we have f of x0 times f of y0 is equal to 0. But using the fact that f of x equals 0 means that x plus 1, we can say that f of x0 times f of y0 is equal to 1. Okay, and what now? That's useless. We know f of x0 times f of y0 is equal to 1. So that's why I told you this is not very useful. But what will be useful is if we take this a plus 1. Now, we will apply the same thing if we can find two numbers x0 and y0 such that x0 plus y0 is equal to a plus 1 and x0 times y0 is equal to b, we can finish the problem immediately by substituting b x0 and y0. How? Well, this will be f of a plus 1, which is f of a plus 1, right? And here we will have f of b, so f of a cancels f of b, but here this will be in the right hand side minus 1. So we will have f of x0 times f of y0 is equal to minus 1. And now, remember this. This f of x equals minus 1 means that x equals 0. So now this is very useful because now you immediately have f of x0 times f of y0 is equal to 0. That means that either f of x0 is equal to 0 or f of y0 is equal to 0. And in both cases you can reach a simple contradiction because if f of x0 is equal to 0, we know that x0 is equal to 1. So that means that x0 is equal to 1. Okay, the contradiction here is y0 is equal to b and y0 is equal to a, which means that a is equal to b, and that is a contradiction. Right? So now, what we have done is if we have two numbers x0 and y0 such that x0 plus y0 is equal to a plus 1 and x0 times y0 is equal to b, then our function is injective for sure. But can we show that we always have these two x0 and y0? Well, let's erase this and try to prove that. Okay, so now we need to show that this equation x plus y is equal to a plus 1 and x times y is equal to b has at least one pair of solutions x0 and y0. It's just like given these two equations, show that there is a solution. right? Okay, how can we solve these two equations? It's very simple. From the first equation, we know that y is equal to a plus 1 minus x. Okay, so that means that here we have a plus 1 minus x times x is equal to b. And this is a very simple quadratic equation. That means that x squared minus a plus 1 times x plus b is equal to 0. So we need actually to show that delta is greater than 0. That's all what it's about. Well, what is delta? Delta here is equal to a plus 1 squared minus b, or minus 4b. Well, here is a problem, because this is not always positive. What if b is very large number? If b is very large, this will be so much negative, and this will be so much negative, so delta is less than 0, and our solution fails. Okay, so the problem is when b is very large. If b is very large, then our solution fails. We can't show injectivity, and thus we can't assume that f is injective and solve our problem, and thus all our work is useless until now. Well, fortunately, we can find a trick here. The trick is to make b, instead of making b very large, make it very small. Well, if b is very large, then we can decrease it actually. How can we decrease it? You might ask. Well, using this. Well, if a and b, and if a and b are these two a and b, and b is very large, then we can simply decrease it, because we can substitute, or we can not. It's not necessary like to use a and b. Instead, we can use a plus n and b plus n. Right? So if b is very large, then we can make it actually small. We can even make it less than 0. If b is less than 0, then this is for sure delta is positive. So instead of using a and b, we'll use a plus n and b plus n, because we know that f of a plus n is equal to fb plus n, and we know that a plus n is not equal to b plus n. So if b is large, then, for example, let's say that b is 100. You can simply subtract 200 from both a and b, and use the value of b that is minus 100, right? So because our n is integer, we can take negative values. So we can simply make n, for example, minus 2b, and this will be minus b, and b will be negative. And now, actually, our work is true, because we now have proven that there exists what? An x0 such that it satisfies this, and thus we can find y0, which is a plus 1 minus x0, and thus we can find a solution x0, y0 to this system, which means that we can show injectivity, which means that our solution, when we have assumed that our function f is injective, is true, and simply we are done. Well, the solutions that we got in this problem were, let's write the solutions. Okay, so let's make a small box here. Remember the first case. In the first case, case 1, we got the solution f of x is equal to 0. And in the second case, we assumed that f of 0 is equal to minus 1, and got f of x is equal to 1 minus x. And since if f is a solution, then minus f is a solution, then the other solution is f of x is equal to x minus 1. I think they are the opposite, but no problem. So in fact, those are the only 3 solutions in our problem. And now, ladies and gentlemen, we are done. So we're finally done. We have finally found our function f, and we have solved this IMO problem 2 from 2017 IMO contest. So let's make actually a quick recap and see what we have done in this problem. A quick revision. So first of all, we found this function equation. It was very ugly. We cannot substitute anything because it's always useless. Then we used the cancelling method which we have learned earlier to get rid of this and to get the beautiful nice f of x times f of x over x minus 1 is equal to 0. And of course we didn't forget that this is true only for real numbers that are different from 1. That was the first thing, the cancelling method. The second thing we did was substituting, was discussing the two cases. Case 1, if we have 1 alpha such that f of alpha times f of alpha over alpha minus 1 is different from 1, then we can substitute x with f of alpha times f of alpha over alpha minus 1 and get f of 0 equals 0 and then prove immediately that f of x equals 0. That's the only case 1. The case 2 was if we have f of x equals times f of x over x minus 1 is equal to 1. Again, for all real numbers that are different from 1. In this case, we immediately found the value of f of 1 because this is 1, so f of 1 is equal to 0. So we found that f of 1 is equal to 0. And we found the value of f of 0 using the fact that substituted x with 0 and we got f of 0 is equal either minus 1 or 1. We took one value minus 1 and used the fact that if f is a solution, then minus f is a solution. So we need only to discuss one case here, which is this. Then we've shown that beautiful, very useful thing that f x plus n is equal to f of x plus n, and we use that a lot. Then we showed that if f of x equals 0 is equivalent to saying that x is equal to 1, and the same if of x is equal to minus 1 if and only if x is equal to 0. And then we showed the injectivity of f, which was the battle, what all the battle was about, proving that f is injective. So we proved that our f is injective using these two things and using the magical x0, y0. The idea was you cannot substitute directly with a and b, then substitute them indirectly, using x0 and y0. So we took x0 plus y0 equals a plus 1 and x0, y0 equals b. And then we have proven that our function f is injective. Then using the injectivity, we crashed the problem by substituting y with 1 minus x once and y with minus x the second time. And then we divided the two equations and we found the value of f. And simply we were done. So yes, ladies and gentlemen, that was our problem for today, IMO 2017, problem 1. So from now on, we'll be moving to much harder problems, like this level. In fact, this is probably very difficult in this level, but we'll keep doing problems from this level from now on. And next, we'll be learning about Cauchy equations in order to move to more advanced problems from the IMO or other contests as well. So if you like this video, like, share, and subscribe to the channel, and see you guys in the next video.